Thanks for joining us for another video. Today we're going to tackle a big question on how do airplanes fly. It has a lot to do with the airfoils, or how the shape of the wing is. So stay tuned for today's video and we'll learn about Mr. Bernoulli. Before we jump into Bernoullis and how airplanes work, let's kind of review what we're talking about, fluid dynamics. So basically, fluids move, or they flow, from areas of high pressure to areas of low pressure. And that typically is caused by either mechanical work, maybe a motor, or say the Earth's spin. Think about it, the Earth is spinning on its axis, and when that happens, it's creating a flow of air particles. So it creates basically areas of high pressure and areas of low pressure. And that high pressure drives out the low pressure, right? It's moving. High pressure typically has nice sunny days. Low pressure is typically more stormy, so not associated with great weather. But it just kind of shows you that fluids move from areas of high to areas of low pressure. Okay, the next thing we need to learn about fluid dynamics has to do with the speed of the fluid. Now, that might be water moving quicker, it might be air moving quicker. So what does that do to the amount of pressure? Here's a quick little example. Say I take a piece of paper and I hold it in front of my face. Now I'm going to make sure my fingernails are side up. And if I were to blow above the paper, so what I'm going to do is I'm going to increase the speed of the air above the paper. What do you think is going to happen to the pressure? Let's take a look. So hopefully you saw exactly what happened. As air moved above the paper, okay, the paper started lifting up, and why? That had to do with a change in pressure. So this comes down to Bernoulli and his principle. His principle basically states that as a fluid moves quicker, it creates an area of low pressure. So when I had that piece of paper and I blew air above it, right, the air was moving quicker, it creates an area of low pressure, so everywhere else is going to be higher, and that is going to pull the paper up, right? The high pressure is pushing to get to where that low area is, so it's going to move that paper. That creates what we call lift. Now, Bernoulli's principle doesn't only just talk about lift or things rising. We said, again, any fluid that's moving quicker creates an area of low pressure. Say I have two ping pong balls here, okay, and they're on the same height. Now think about it, if I want to blow the air between them, I'm going to increase the speed of the air particles between. So that's going to, again, based on Bernoulli's principle, there's going to be an area of low pressure between. That means everywhere else is going to be higher. So what's going to happen? That high pressure is going to want to move towards the middle. It's going to end up pushing the ping pong balls. So take a look. Exactly what should happen. As the particles move between, right, low pressure, and the balls actually moved closer to each other. Now when we talk about fluid dynamics, I have to bring up the lazy river, my favorite part of a water park. Now I have kind of a nice little simulation going for you, and I'll put the link down below. But say I were to take a lazy river, and all the red dots here look like the tubers, so picture everybody's on a red tube. And if I were to make the lazy river wide in some areas and narrower in areas, what's actually going to happen to the speed? Okay, maybe you've seen it. Usually the wide areas where people are getting in and out. And you can see there the speed is actually slower. Right, so the normal width, okay, it's cruising along. You get to a wider section and it actually slows down. Now if I get to the narrow section, right, and this is usually where the rapids are, things actually increase in speed. So how does that affect pressure? Think back to Bernoulli now. Okay, what happens is when things are moving slower, the pressure is actually greater. There's almost like more of a buildup, right? Like things are almost going to start clogging. They're moving slow, so things are going to get pressed from behind. Now, when things get narrow, okay, things have a lower pressure, right? Things are like immediately kind of sucked into the area because it's lower pressure. So you can kind of see that in the simulation. I hope you guys can take a look at that on the website, to the link down below. You can play with different fluids, different speeds. You can change all sorts of designs to this pipe instead of lazy river. But hopefully this gives you a good visualization and some good data to show you again that the higher the speed, the lower the area of pressure around it, so things want to rush into that area. Alright, our last example before we get to an airplane, alright, has to do with an ultimate disc, or a frisbee disc as you might know it. Now, if we take a look at the design, it was designed in a particular way to work with physics. So it's actually proving a lot of physics concepts. We're actually just taking a look at Bernoulli's, which has something to do with kind of what we call an airfoil. Now if we take a look at the shape of the disc, it's actually round on the top and it's actually pretty flat along the bottom, and it's designed on purpose. So if I had air particles moving across the disc, you're going to see the ones that are hitting the very front edge have two directions. You can go either above the disc or below the disc. Now, it's almost like saying, hey, you came to a fork in the road. You either have to go the roundabout way, or you can go maybe a step down and you can go straight through. And that's exactly what happens to the disc. The particles that are going above the disc have to go a further distance. And they play this game of kind of almost like catching up, right? They have to move a little bit quicker because things are getting pushed from behind. So, what happens is, as the particles have to go a further distance and have to kind of speed up, we talked about it creates an area of lower pressure. Again, it's a fluid, air is a fluid, air dynamics, right? It creates an area of low pressure above the disc. That means it's a higher pressure below, and it creates a lift. So basically the disc is moving upward. So as long as the disc is moving forwards and has enough velocity, it's going to continue to have lift to go up or to stay up, to kind of fight against gravity. Okay, we finally made it to the airplane. All right, let's talk about it. All right, so instead of drawing a picture of an airplane, we drew a cross-section of the wing, and we call that an airfoil. Basically, an airfoil is a cross-section of an object where it shows basically the airflow or the aerodynamics behind it. So in this case, okay, we're looking at a cross-section of the wing, and very, very similar to a ultimate disc, okay, we're going to see that the shape of the top of the wing is different than the shape at the bottom, okay, and it's built like that for a reason. Now I do want to put a disclaimer. We are talking about Bernoulli's principle, and there's multiple laws and multiple principles that go into why a plane flies. We're going to look specifically at Bernoulli's though right now. So if anybody says Bernoulli's doesn't have to do with flight, it does. It's not 100% the reason why planes lift off the ground or why they kind of go against gravity, but they do have a huge role in it. Similarly to an ultimate disc, right? When we have a cross-section of the wing, air flows above the wing, and again, it has to travel a further distance. Now it's a little bit behind, but it actually goes faster. So again, we're creating an area of lower pressure above the wing, so that creates an area of higher pressure below it. So if you think about it, the faster the plane's going, the bigger the difference between the low and the high pressure, right? So that means if a plane's going a little bit slower, that pressure difference isn't going to be there. Matter of fact, if the plane stops, okay, it's not going to be lifting. Okay, hopefully that makes sense. So again, we have area of low pressure because the air is going faster above the wing. It has to travel a further distance. And then below it, we have higher pressure, so that creates that lift. Now, as I mentioned, okay, there is more to it than this. If you guys remember Newton's third law, every action has a reaction. This has to do with what we call the angle of attack for a plane wing. If you're looking at the kind of illustration, okay, the wing is tilted at an angle, and the reason for that is as air particles hit the bottom, they're angled away. So again, if there's if I keep throwing rocks at a frisbee, it's going to keep pushing the frisbee upward if I'm throwing the rocks from the bottom. The same way, these particles, as they hit the bottom of the wing, they're pressing the plane upward. Okay, so that has a lot to do with the angle of attack. Hopefully you see that Bernoulli's principle and this angle of attack, which is kind of Newton's third law, action and reaction, they are the bulk of the reason why planes fly and why they lift off the ground. Right? We also mentioned, again, the slower they're going, the less of that force going upward, all right, and that's the reason why gravity is going to win. When we're going slower, the plane's going to kind of descend on its own. Okay, so the next time you see an airplane wing, take a look at the shape. Okay, take a look at, hey, how is the shape on the top different than the shape on the bottom, and why is the airplane wing tilted? So hopefully you enjoyed today's video on Bernoulli's principle. Hopefully we're kind of wrapping up fluid dynamics so you get a better understanding of how that works. Take a look again at the simulation, go play with it, see how you can change the fluid, the speed, and what happens to the pressure. Thanks for watching today, and hope you enjoyed.